We have 4 scientists representing the BICEP2 Collaboration. John Kovac from the CFA is the principal investigator of the BICEP2 telescope located in Antarctica. Chao-Lin Kuo from Stanford University and from SLAC is project co-leader and leader of the next telescope in this series, BICEP3. Jamie Bock from Caltech and JPL, project co-leader and developer of the foundational detector array technology. And Clem Pryke from the University of Minnesota, leader of the analysis team that's producing today's results. And we've also have here Marc Kamionkowski, professor of physics and astronomy at Johns Hopkins University, who is an external expert, completely dispassionate, who can comment on the results. And once again, I'll hand over to John.
Here today and to be able to present to you the results that we've worked very hard to produce over the last 8 years, the 4 years specifically working with this data from the BICEP2 telescope. This is an extraordinary telescope pictured behind me that's situated at the South Pole Station in Antarctica, the National Science Foundation's Amundsen-Scott South Pole Station. And what this telescope does is it measures the cosmic microwave background radiation. That's the oldest light in the universe. It was emitted 380,000 years after the Big Bang, when the universe was in a hot, dense, early state. And BICEP2 is designed to search for patterns of polarization in that light. So you see behind me such a pattern depicted as lines on the sky above the BICEP2 telescope, and that's the actual BICEP2 polarization map that's been projected up there. So in particular, BICEP2 is looking for swirling components to those patterns called B-modes. So the theory of cosmic inflation, which attempts to explain the start of the Big Bang itself, predicts that the early universe will contain a background of gravitational waves that produce such a swirling B-mode pattern of polarization, particularly on angular scales of a few degrees on the sky. And today we're going to be reporting the detection of B-mode polarization as seen by the BICEP2 telescope that matches very closely the predicted pattern. Okay, so our team, which is shown in part here in this photograph, has just posted online scientific papers and all of our data products describing our observations. And before we go into details talking about those, let me introduce who the team is. So the 4 up here today are the co-leaders of the BICEP and Keck array series of experiments of which BICEP2 is a part. So I'd like to highlight contributions from other major collaborators that you see in BICEP2 over the past years, including UC San Diego, Brian Keating's group there, the Leonard Bond's group from CEA in France, NASA's JPL, Ken Irwin's group at NIST, Peter Ade's group at Cardiff University, Bart Netterfield's group at the University of Toronto, and Mark Halpern at University of British Columbia. So those are all the senior people, but what we really should do is we should highlight how many young people in science have started their careers off by dedicating years of effort to making this project possible. So you see here depicted photographs of the BICEP2 postdocs and graduate students. These are the people who have dedicated their fellowships or their PhD theses, years of effort to making these projects work over the past 8 years. And also, a project like this doesn't happen without somebody volunteering to spend a 6-month-long night at the South Pole, the so-called winter over, who operates the telescope on his own at the South Pole for the 9 months of the year, actually, that it's inaccessible. And so for the BICEP2 project, the winter over in 2010 was Stefan Richter, and the winter over in 2011 was Stefan Richter. And the winter over in 2012 was Stefan Richter again. And Stefan is here in the audience. And he's still smiling, so it's amazing. Okay, so BICEP2 is the second telescope in this series, the BICEP and Keck array series of telescopes. So the first in this series, BICEP1, observed at the South Pole from 2006 to 2008. It was very successful, and it set the best previous limits on this B-mode pattern of polarization in the sky. So we parameterized the amplitude of that B-mode pattern in terms of the ratio of gravitational waves that it would produce compared to the ratio of regular fluctuations, density fluctuations in the universe. That ratio R was constrained by BICEP2's measurements to be less than around 0.7. Less than exactly 0.7, in fact, at 95% confidence. So BICEP2 picked up where BICEP1 left off, observing from 2010 to 2012 for 3 seasons at South Pole, New technology allows it to be 10 times faster than BICEP1. And we've already made BICEP2 obsolete. The Keck array started observations a couple years ago at South Pole. It's got essentially 5 BICEP2s observing on the sky at the same time, trained on the same patch. It's 5 times faster than BICEP2, and it will soon be joined at South Pole by BICEP3, the third in the BICEP series and 4th in this series of experiments. Okay, so what does our experimental strategy look like? Behind me, you see the South Pole station itself. You see the living quarters. I believe it's on the left of the screen, and a runway where the planes land, running down the middle of the screen. And to the right, you see all of our observatory buildings. And on those observatories, we have our telescopes. They're all small aperture telescopes that are targeting this science goal. So these are not big dishes that we are using for our experiments. They're optimized to target the 2-degree scales on the sky, where the B-mode signal from inflation is expected to peak. And they integrate continuously from the South Pole. An extraordinary thing about the South Pole is that the sky rotates around a point above your head. So if you want to train your telescope on one patch of sky and collect photons from the CMB on that patch of sky for a long period of time, you can do it 24 hours a day, 365 days out of the year. You just have your telescope track that field around the sky, and you can see our telescope scanning back and forth on that small patch of sky and moving with it as it tracks around. So this is what the Keck array telescope looked like last week, scanning at the South Pole. BICEP had a similar strategy here. We call this relentless observing. And this is what it looks like now before the sun goes down. But at the South Pole, once the long 6-month night begins, you get sometimes these really spectacularly beautiful skies above. So the thing that's dominating the brightness of this sky is the aurora. But you can see, and our telescope isn't affected by that, but you can see also rising almost vertically above our observatory building the plane of our own Milky Way galaxy. So when you ask, what is the small patch of sky that we train our telescope on? Well, what we try to do is we try to point as far away from that Milky Way galaxy as possible, because that Milky Way galaxy, in microwave emission, actually has a non-negligible contribution to the radiation, radio emission and dust emission in our galaxy. It can be polarized and can confuse these B-mode measurements. So we pick a patch of sky that is the so-called southern hole, the cleanest patch of sky that we can train our telescope on. And we observe that relentlessly for 3 years straight. So I'll hand it over to Chao-Lin now.
So it's pretty interesting that I get the part that's already pretty well covered and explained in all the rumor web pages out there. But I'll do my best. So our general scientific strategy is to use the gravitational wave background that can travel across the entire history of the universe. And we use that to study the very first moment of Big Bang. So you can't quite do it with just photons because, as John said, cosmic microwave background was the oldest light from the universe, but it's not old enough for us. It was already when the universe was 400,000 years old. We want to study the very first beginning of it. So you can think of cosmic microwave background. Before that, everything was ionized with charged particles, making it opaque to photons. So as a curtain of something, you can learn a lot from microwave background, but it also blocked the view, the very first beginning from us. So if you take gravitational wave instead, because the early hot, dense stage is still transparent to gravitational wave, you can use it to directly see what happens at the very first beginning. So in this picture, it shows, it reveals the inflation process. So how do we do that? Gravitational wave leaves a very specific imprint, as John just said, of a swirly pattern on the polarization state of cosmic microwave background that we call B modes. And it looks like that on the screen, this swirly pattern. And by looking at that, the images of those swirly patterns, you're directly making images of gravitational waves created at the very first moment of Big Bang. So I always thought of inflation as the bang of Big Bang. I'm not sure, what the big part is about, but inflation is the bang. So inflation was proposed in late 70s and early 80s to explain a series of classical problems in cosmology related to the expansion of the universe. I'll just give an example. Why was the universe created so uniformly? And the solution that inflation proposed was if the universe went through a rapid spatial expansion, like what's depicted here, then this superluminal placement of regions can set up the right initial condition to give us a uniform universe. This is a pretty hard concept, but I'll just leave it at that without going into great details. So there's one more amazing thing that inflation does. It's the generation of perturbations. So according to Heisenberg's uncertainty principle, there is vacuum fluctuation even in empty space. So the field that was responsible for inflation, which we call inflaton, has that vacuum fluctuation. And the rapid expansion of inflation pretty much just amplified or stretched that initial 0-point fluctuation into density fluctuations studied by Planck, WMAP, SPT, ACT, and many other experiments. And those are the seed for structural formation. It creates, under gravitational instability, it creates galaxies, clusters, and so on. So it's a very important part. So today, we've detected the other half of inflation. So gravity, the 0-point energy of gravity, has fluctuation as well, as we think. And inflation can, again, amplify that, stretch that, to make it a classical gravitational wave in the early universe. And that's exactly what we see with BICEP2 in the polarization of cosmic microwave background. So basically what we did today was to discover the other half of inflation, completing the picture, the paradigm of inflation. We verified the existence of a new field, a new particle, if you will, inflaton, and we set the energy scale at the grand unification scale. So that's what we did. So as John and others mentioned a few times, when this picture was proposed in late in 80s, people thought there's no way to distinguish density perturbation from gravitational wave. But in 97, several clever theorists came up with a method. So they realized you can separate, and Marc Kamionkowski is one of these brilliant theorists here with us, and he will comment. So they realized if you linearly decompose the polarization pattern on the sky into a mode called E mode and a swirly pattern, B mode, and density perturbation, the mundane type of perturbation that we know of, can only generate E mode perturbation. And gravity wave can generate E mode and B mode. So if you see B mode, the only possibility on these angular scales, at least, is coming from a gravitational wave. So by imaging B mode, you're directly seeing images of gravitational wave in the CMB. So that's all very nice. So the pattern is very distinct. However, the signal is very small. Okay, so you're trying to measure the polarization. So you often do that by turning a polarizer 90 degrees. And the level of polarization that BICEP just reported corresponds to about 1 part in 30 million. That's different in power in vertical versus horizontal. So while this is a nice theoretical prediction, and the hunt was on since 97, it took us 17 years to get here. And we did so with modern technology that Jamie will describe.
Okay, thank you, Chao-Lin. Now that Chao-Lin's described what we're trying to detect, I'm going to say a few words about how we do it. So BICEP was invented in 2001 with a single goal in mind, and that was to make the deepest measurement technologically possible of an inflationary polarization signal in the microwave background. BICEP was really the first experiment of its kind, and it was based on a radical concept, which is to use a small telescope with just enough resolution to detect the polarization fluctuations where they're brightest at an angular scale of about 2 degrees. Now that small telescope is two lenses like a spyglass, and the primary aperture of our telescope is about 26 centimeters. But don't let its small size fool you. Our telescope has enormous light gathering capability. And so in fact, the field of view on the sky is 20 degrees across. And with a small telescope, we can do things that are simply impossible to do with a large telescope. So the first thing we do is we take our small telescope and we cool it to 4 degrees above absolute zero. And then we surround the telescope with absorbing material which soaks up any stray radiation. That's very difficult to do with a large telescope, of course. Furthermore, with a small telescope, we can pick up the whole telescope and spin it around its axis to remove any polarization properties that might be associated with the instrument itself. The optics of this instrument, as I mentioned, are these two lenses, but they're designed to have a focal plane that's flat, which meant that when the best technologies came along, which we were developing back in 2001, they would just pop right into the focal plane, and in fact, that is what happened. And finally, in order to achieve the sensitivities we need, the focal planes cooled down to just 0.25 degrees above absolute zero. Okay, on the left is showing what a state-of-the-art focal plane would look like in 2005, and that's the BICEP2 focal plane. It has about 100 detectors, and that was state-of-the-art at the time. The detectors in this telescope are actually limited to a large extent by photon noise from the background it observes. And in fact, we can build detectors that are limited by photon noise from the microwave background itself in space. So the name of the game is to build more detectors. It's a challenge that might be similar to taking what was film in an analog camera and making an array detector out of a CCD chip. But in fact, the problem is actually much more difficult. The focal plane on the left is not just like the film in the camera, it's like the camera. The focal plane actually gathers the light, chooses the wavelengths that are observed, it analyzes the polarization, it detects the radiation, and it amplifies the signals. And so the question is, how could we mass produce such a technology? And so the focal plane that you see on the right basically is an approach of building that camera on a printed circuit board so that it can be mass produced. The BICEP2 focal plane on the right has 512 detectors, and as a combination of the detectors being somewhat better and having more detectors, it makes observations 10 times more quickly than BICEP1. So an observation, the data we have with 3 years of BICEP2 would have taken 30 years to obtain with BICEP1, and while I love the poll, that's a bit too much. Another point here is that these approaches are actually quite different, and in our results, we compare the results of the two experiments, and they agree, which leads credence that the properties of the instrument are well controlled. So how do you make a camera that detects polarization at 250 millikelvin on a chip? The answer is to use superconductivity. And briefly, our approach is the lens of the camera is replaced by what is essentially a circuit board printed antenna. The antenna gathers the light, chooses the spectral band, and that light from the antenna is passed to a detector. And this process is all built by photolithography, so it can be mass produced. This is the sensing element at the end of the detector, and at the end of the antenna. And basically what happens is that microwave background light propagates through the antenna to a suspended island of material, thermally isolated by tiny threads of a film. And the power from the microwave background is dissipated, it's turned into heat, into that meandered resistor. And that heat is then sensed by a superconducting thermometer biased just on its transition between normal and superconducting state, and read out with a series of superconducting amplifiers developed at NIST. This map just shows our observational data as time goes on here, this movie. And what you see on the left are our signals. It's decomposed into two polarization states. So as time goes down, the time goes on, the signal becomes more and more apparent. And the right is showing a difference map, which should be consistent with 0. And one can see the noise getting smaller and smaller and smaller. I should say that the noise in our maps, we achieve a sensitivity below 100 nanokelvin in a square degree of sky. That's 100 billionths of a degree Kelvin on top of the 2.7 Kelvin CMB signal, with a total combined sensitivity of about 3 nanokelvin. The pattern you see in these two polarization signal maps, you can see on the top figure it sort of has a vertical horizontal pattern, and the bottom map looks kind of like chicken wire with a cross pattern. And those patterns are characteristic of our signal being dominated by the E-mode polarization pattern that Chao-Lin mentioned. But lurking beneath that is a B-mode signal.
Okay, so this is the actual polarization pattern map as measured by the BICEP2 telescope. So this is the total polarization signal. It's basically the previous map turned into little, call them pseudo-vectors, little lines, illustrating the direction at which the polarization is oriented from different points on the sky. So the x-axis is one direction on the sky, the y-axis is the other direction on the sky. It's a map, a polarization map of the sky. The most sensitive polarization map ever made at these angular scales. You can see there the scale at the top is showing you how long, so a long line on this plot is 1.7 microkelvin, 1.7 millionths of a Kelvin. And so that's the raw map that we've measured. And you can see that it mostly has a kind of, well, it mostly has a non-swirly pattern, right? If you look at where the lines are big and where they're small, and then you look at the direction of the lines moving from a region where they're big to small, the lines are either parallel or perpendicular, or at 90 degrees to that direction. So this is the E-mode pattern. This raw polarization pattern is dominated by the so-called E-mode pattern. And that E-mode polarization a few years ago was fantastically hard to measure and fascinating scientifically. But now it's just getting in the way of measuring the thing that we're really after, which is the B-mode. So times change very rapidly in this field. So taking that pattern and subtracting away the E-mode, we do this. Okay, so we mathematically operate on the map to remove the E-mode pattern, the part of the pattern that we're not interested in, and that leaves behind the B-mode. So the swirly part of the pattern that we are interested in. And you can see that that's a very small fraction. So this is a very difficult experiment to do because we need to achieve very high fidelity, not just very high sensitivity, as Jamie has just emphasized, but very high fidelity. If each of those little polarization vectors was twisted by even a few degrees away from the true direction, then the amount of B-mode, the amount of swirliness in there will either be exaggerated or possibly cancelled out. So it's fantastically important that we achieve very high fidelity. So we have labored long and hard. We've been working on this data analysis for about 3 years straight, a large team of people, as John emphasized, trying to do all possible cross-checks and data slicings that can convince us that we really understand every aspect of the instrument sufficiently well, and that there really is no false polarization that's being introduced there, or any kind of distortion of the pattern that would induce a false B-mode. So we're firmly convinced now that the B-mode that's left when we remove the E-mode is truly there. It's truly on the sky, as we like to say, which means it's out there coming to us from the universe, right? Rather than being induced in the instrument or maybe by contaminating emission from the ground. So let's flip the scale. So going from this slide to this slide, all we're doing is we're just amplifying the scale. So the scale is going from 1.7 microkelvin for a full-length vector to being 0.3 microkelvin for a full-length vector. So basically like a scale up a factor 6.
So you can see that when we do that, the swirliness of the pattern is thrown into stark relief. We can see that indeed this is the swirly pattern that we're after. And what we've done is very carefully shown that this pattern is in excess of noise. It's not coming from the instrument. It's really coming from the sky. So then the question is, what is it? And we've done many further studies to try and convince ourselves that it's not foreground emission from our galaxy, because our galaxy also emits at these wavelengths very, very weakly, but the signal that we're after is so weak that it could potentially still be a problem. So we are convinced on the basis of all of the studies that we've done that the signal is real. It's coming from the sky, and it's coming actually from the microwave background itself, from that 400,000 years after the beginning point. As Chao-Lin emphasized, by far the most reasonable interpretation of such a signal is that it is gravity waves written in that last scattering surface pattern, in that microwave background pattern, and those gravity waves come from the inflationary epoch at a tiny, tiny fraction of a second after the beginning. There's one final slide here where we add color to it. The color is really the B mode itself. And you can see that if you look at the vector pattern around, for instance, a hot spot, a red spot, we have an anti-clockwise circulation pattern. And around a cold spot, a blue spot, we have a clockwise circulation pattern. So that's exactly the pattern that we're looking for. Now, these following two plots are a little hard to explain to a non-specialist audience. Multipole number is angular scale, going from large angular scales at low multipoles to high angular scales as you move to the right. On the axis. The angular scales that we're most interested in are about 80, and that corresponds to an angular size of about 2 degrees on the sky, which is about 4 times the diameter of the full moon. The data points are the actual measured data points, and here we have data points from BICEP2 alone, the first set of points, and then also BICEP2 in cross-correlation with BICEP1 and in cross-correlation with the Keck array, the third-generation experiment that John mentioned. The colored lines, the red lines, are the theoretical expectations. The lower one, where it says B mode from lensing, that's the theoretical expectation if there is no gravity wave signal. And then the dashed line adds in the theoretical expectation from a gravity wave signal. And so you can see that the data points basically sit on the dashed line. And so this is a very high confidence detection of an excess in just the place where we expect it. If in fact there are these gravitational waves from inflation. So this final plot is the same data plotted again, but now on a logarithmic scale. I'm not going to go into too much what that is, a kind of powers of 10 scale. And you can see the data points from previous experiments as the massive colored points. And those were upper limits. They were setting limits that, okay, if there is a gravity wave signal, it has to be smaller than the position of the point. In a downward direction. But now finally, with these BICEP2 results, we have for the first time an actual detection of the mythical gravity wave signal that people have been searching for so hard for so long. Now, we may be the first, but there are many experiments coming down the line, many competitors out there. They've actually mostly been focusing so far on measuring the B mode from lensing at those smaller angular scales, at those higher multipole numbers. But they will certainly soon be confirming our result, we hope. So there's many more experiments coming, SPT-pole, ACT-pole, EBEX, Piper, I don't know, I'm not going to get them all, I'm sorry, there's quite a number. Okay, so that is our conclusion, and turn it over to Marc. He can tell you what to think about it.
Okay. So it's not every day that you wake up and learn something completely new about what happened 1/trillionth of a trillionth of a trillionth of a second after the Big Bang. And I don't think that you need to be a professional cosmologist to think that's really cool. So just to clarify, I'm not a member of the collaboration, as you can tell, because I'm not wearing one of these nifty T-shirts, which they sell only at the South Pole. So, inflation has for some time been something to be taken quite seriously, especially after the transformative results that we've seen from cosmic microwave background measurements the past decade and a half, and in which, for example, Jamie played a particularly important role. The issue, though, is that inflation requires some new physics beyond the 4 fundamental forces that we know about. So over the years, theorists have developed a ton of ideas as to what this new physics might be, but until now we've had no way to discriminate between these different ideas. This gravitational wave signal that they've detected, though, can help us out. The strength of the signal depends on how energetic inflation was. Inflation models span a huge range of energies, and so a precise measurement of the energy very dramatically narrows the range of inflationary models. In particular, this measurement suggests that inflation may have had something to do with unification of the strong, weak electromagnetic forces, ideas that particle theorists have been entertaining since the 1970s. So, this detection is cosmology's missing link. It's something that we thought should be there, but we weren't really sure, and it has been eagerly sought now for close to 2 decades. This is not something that's just a home run, but a grand slam. It's the smoking gun for inflation. It hints at unification of fundamental forces at energies 10 trillion times higher than those accessible at the Large Hadron Collider at CERN. Since these gravitational waves are produced by a Hawking-like process in the early universe, we're seeing Hawking radiation here. And this is also the first detection of gravitational waves, a consequence of Einstein's general relativity, which next year will be 100 years old. Of course, as Carl Sagan said, extraordinary results require extraordinary scrutiny. And these results are as extraordinary as they get, and they will require the most extraordinary scrutiny. So we must therefore wait before buying any tickets to Stockholm to really, or to reach these dramatic conclusions until these results are vetted fully by the community and verified by other groups. If these results hold up, and as far as I can tell from the presentation that we've seen today and the paper, these B modes quack like a duck, then we've learned only that inflation has sent us a telegram encoded in gravitational waves and transcribed on the cosmic microwave background sky. It will be essential in the years to come to follow through with more detailed and precise measurements to infer fully what this telegram is telling us.
Hello, everyone. I am Christine Pulliam. I want to begin by thanking our presenters for taking a very complex subject and making it more understandable. There has been tremendous interest in this out in the wider community. In fact, I'm told that we brought Harvard servers to their knees with the webcast of these events. Not to worry, it will be archived online afterwards. So at this time, we are going to take questions from the media. We will begin with the media who are in the room here and then move on to email questions. I want to ask that you state your name and affiliation and wait for the microphone. So do we have any questions from the media in the room? Yes. Courtney? No, microphone. Thank you.
Hi, Camille. Is this on? Yeah, I just can't hear myself. Hi, it's Camille Carla from Sky and Telescope. I have 2 questions. One, what is R? It sounds like it's a relation between the density fluctuations in the early universe and the gravitational waves themselves. Could you clarify? And there are a lot of experiments looking at this one particular section of sky. Why you, and who's going to be able to confirm it?
Okay. Why don't we start with the R? What is that?
So R is the letter that follows Q and proceeds. So what they've detected are gravitational waves, and gravitational waves are propagating ripples in space-time. And R is just a parameter that quantifies how large those ripples are. Are they very, very large ripples, or they're very tiny ripples? And so R of 0.2 by our standards are pretty big.
I can take the second question. Part of the reason why us is that when we started this experiment in 2001, we were pretty much the only experiment in the field. And so we had several years of a head start running our experiment in Antarctica. Our field is covered by another experiment, which is the South Pole Telescope. We had coordinated with them last year. And of course, by the Planck satellite, which covers the entire sky.
Okay, thank you. There's a question right next to her.
Test, test.
Hi, I'm Lisa Grossman from New Scientist, and I want to know more about the physics beyond the standard model implications of this and the grand unification. Generally speaking, what else beyond the standard model and of grand unification theories can we learn from this with future studies of this signal if it's confirmed?
So right now, I think what we have are hints. So as I said, this experiment actually measures that value of R actually is proportional to the energy density of the universe at the time that inflation occurred. And all we can tell now is that the energy density was comparable to what you would expect from grand unified theories. We can't really say anything beyond that right now. We can't tell anything about the details of grand unified theories. With future measurements, they are going to be able to measure this gravitational wave amplitude, or in other words, these B modes, as a function of that multiple parameter in the plot that Clem was discussing. So as you go to the left on that plot, lower values of L, you're looking at larger angular scales, you're looking at larger features, and in some sense you're measuring the energy density of the universe at earlier times. So in the future, if this signal is confirmed and extended, we will have not only the energy density of the universe at one particular time during inflation, but at a multiple set of times, and we'll begin to learn something else about how inflation evolved, and then perhaps begin to learn more about the physics that may have given rise to inflation.
Other questions? Yes, Maggie. Microphone, please.
Thanks. Maggie McKee, I'm freelance. If this signal is confirmed, does that basically mean inflation, there's no uncertainty at all that it happened? And how would you go about kind of figuring out what inflation was? And how will you do that from now on?
Guess I'll go. So physicists, the job of a theoretical physicist is to construct a mathematical model that matches the measurements and observations. And when we have a lack of data, then there are many models that can describe the observation. And as we accumulate more and more data, the range of models that can explain all the data becomes narrowed. And then we begin to have confidence in any particular model. So as I said, I think we've had good reason to believe for a decade and a half that inflation looks, predictions of inflation look quite a bit like what we see in the universe. But we've had many, many different models of inflation. Inflation, in some sense, is a paradigm or idea, and there have been tons and tons of very speculative ideas for inflation. And what's happened now is that the number of models that we have is not this big. The number of inflation models that we have now is this big. And that's a sea change from last Friday to this afternoon.
Other questions? Ron.
Ron Cowan for Nature, and I guess for Marc, what theories or models of inflation are ruled in? Which ones are ruled out? And in doing so, what is that telling us about what was going on at that first tiny fraction of a second after the Big Bang?
So there are more models that are ruled out, I would say, than those that are ruled in. So one very simple classification that theorists have is large field models versus small field models. So there's this new scalar field, or a Higgs-like field, which we call the inflaton, for lack of a better name, that moves, that rolls during inflation. And the large field models require that inflaton field move a large distance. And the small field models require that the inflaton move a small distance. And many theorists until now have thought that the large field models don't work because they're unstable to quantum corrections. But what this measurement suggests is that inflation did proceed by a large field model. So there's something about quantum mechanics and the stability of these theories that we've learned that we did not know before. As far as inflation models that have been ruled out, there have been many models of inflation constructed over the years, and over the past year in particular, they've received a lot of attention because Planck actually placed this fairly stringent upper limit on the gravitational wave amplitude. And although it wasn't that stringent, I think many theorists began to lose confidence that these gravitational waves might actually be there. And so there's been a focus the past year in particular on models of inflation where the energy density of the universe during inflation is not too much higher than what you would expect from the type of physics, electroweak unification being probed at the Large Hadron Collider. So now we know conclusively with these new results that those models are no longer viable.
Are there other questions in the room? Okay. Then we can proceed to online questions.
Sure. We have one online question from Live Science from Tanya Lewis. The question is, can you please elaborate on the impact the discovery will have on physics and cosmology?
I could have a go. So I think we should think of this this measurement today as opening a new window up on what we believe to be a new regime of physics, the physics of what happens in the first unbelievably tiny fraction of a second in the universe, and at extremely high energies, apparently at energies that are comparable to the grand unified theory scale. So there's a lot more to be done there with that signal. A signal of this size, as Marc was saying, could offer us a wealth of information about how the processes proceeded during inflation, how the energy density of the universe evolved during the times that the observable scales in our universe exited that horizon. And that has the potential to teach us a lot about physics at the highest energies, physics at the extreme frontiers. I think that many people will tell you also that it's an interesting implication of the apparent existence of gravitational waves from inflation, that the gravitational field itself is quantized, and that the waves that result, that are frozen on cosmological scales, are observable as a pattern today. You want to try to add to that?
Yeah, I just wanted to ask something. So I received emails this morning about a conference being organized on this subject before this press conference.
So one thing to emphasize is that whilst this result is great, and we'll certainly go out and have some drinks tonight, we're not completely done, right? So as has already been alluded to, there's more that we can measure. By measuring at the very largest angular scales with Planck, Space Mission or its successor, or maybe even ground-based experiments, we can measure the signal over a longer lever-arm, over a wider range of angular scales, and that, as Marc was saying, gives us additional insight into the physics of inflation. So this is not the end. This is the beginning, as John said.
Yes, back in the, I think that's Alan, behind the light.
Yes, Alan McRobert, Sky and Telescope. This may be very speculative, but being able to probe into the physics of the time of inflation, does this open up maybe a route to what came before that 10 to the minus 34th second? Does it say anything about the multiverse ideas, eternal inflation?
No one on our team is allowed to answer this question.
Marc's going to tell us what signal we detect.
So that's a great question. So one way I like to describe inflation is as the mechanism that set the Big Bang in motion. And it's perfectly natural to ask, well, if inflation set the Big Bang in motion, what set inflation in motion? And I don't have an answer to that. There are many theorists who have many speculative ideas. Some involve the multiverse. I don't think that this measurement says anything concrete about the answer to that question. But by narrowing the range of inflationary models so dramatically, it allows us perhaps to focus more on a more specific range of inflationary models. And there's some hope that maybe, although maybe I or nobody else in the room has a good answer for that, maybe within the coming years somebody else will have a good answer to that. So That's my answer.
I would just like to mention that as an experimentalist, I'm firmly opposed to theories which have no observable consequences.
As a theorist, I should say that when inflation was proposed 30 years ago, it was a figment of theoretical imagination. And, but it was a really interesting idea. And in the years shortly thereafter, the creators of inflation, and as well as other theorists, worked out a number of predictions of inflation, some of which could never be tested, but others which could be tested. And, you know, all of the naysayers 14 years ago had their mouths shut by measurements from CMB fluctuations. And I think about a decade and a half after the introduction of inflation, my collaborators and I, Arthur Kozowski, Albert Stebbins and I, and also Urs Celiak and Matthias Aldariaga, worked out papers where we said that, you know, here's another measurement that you can do to test inflation. And what I'm hoping is that, you know, with these results, there will be other theorists out there who start to think deeply about these questions about how inflation might have begun, about the multiverse, and perhaps think up new ideas about how that question can be addressed, so that 20 years from now we'll have a press conference saying we have firm evidence for the multiverse.
Or against it.
I believe that Professor Lindy would like to comment on that. One of the developers of the theory of inflation.
Hi. When inflationary theory just began, we did not really know whether it will be related to the theory of the multiverse. But then very soon after it evolved and new versions were developed, and in particular the versions which have been confirmed by the recent data, in most of the models of inflation, if inflation is there, then the multiverse is there. It's possible to invent models of inflation which does not allow multiverse. It's difficult. So every experiment which brings better credits to inflationary theory brings us much closer to the establishment of the proof or to the just hints that the multiverse is real.
Dr. Guth, do you have anything to add to that?
Microphone? Well, I just want to say I agree with Andre that it's hard to build models of inflation that don't lead to a multiverse. Not impossible, so I think there's still certainly research that needs to be done. But most models of inflation do lead to a multiverse, and evidence for inflation will be pushing us in the direction of taking this multiverse idea seriously.
Do we have any other questions here? Yes, we do have one in the back. So we can borrow the microphone back. Thank you. Over there.
I'm Carolyn Johnson from the Boston Globe. I was just wondering if you could describe a little bit about the process. When in the 3 years of data taking did you begin to realize you might have this signal, and how did you react to that, and how long did you spend troubleshooting it, making sure it was real, just kind of what the process was like?
I think Clem should answer this.
Well, it's been a tremendously exciting process. It's been described at times in our group as an emotional roller coaster. So the signals kind of gradually emerged out of the fog over a period of time. There was no one specific moment. There were some very important moments where we first decided to take cross-spectra between our data and the BICEP1 experiment. So that was a kind of watershed moment to see that there actually was cross-correlation. Again, the cross-correlation against the Keck array that we did rather late in the game was another kind of watershed moment. But basically, we're all intensely skeptical, and of course, you know, when we first saw hints of a signal, we totally didn't believe it, and we were trying to find, well, what is it? What's wrong? Is it this systematic? Is it that systematic? So I don't know. I think even I would have to go back and review all of my emails and meeting notes and try and pin down where the moments were. But basically, confidence built over a long period of time, fueled by various cross-checks and particular studies. And, you know, it's mind-boggling to go looking for something like this and actually find it, right? It's like theorists like Marc are forever setting the experimentalists' wild goose chase missions. The world of experimental physics is littered with guys who spent decades searching for something which turned out not to exist, right? So it's just been a really incredible experience to actually find what we were looking for. I mean, of course, we write grant proposals and we make it sound like we're going to find it, right? It's one thing to say that, and then it's another thing to really believe it in your heart.
This is being recorded.
No, look, I mean, seriously, when we write the grant proposals, we intellectually believe it, right? But I don't know, maybe I'm just a pessimist, and so I find it hard to believe it for real, but it's been amazing.
I distinctly remember our collaboration meeting last year, where the first half of the meeting, we had been thinking we got to get a paper out, and let's just try and set an upper limit, and the data wouldn't cooperate. And then the second day, I think somebody showed a cross spectrum, and it just dawned on everyone, well, maybe this really is real. And then we had this 1-year odyssey of doing all the checks that Clem said.
Yeah, there is variation among the four of us, and everybody in the collaboration as well. I think me personally, I started to think maybe this is real about 6 months ago, 50-50, and that became 90 and 95 and so on. More recently.
That was part of the process and part of the strength of having so many of us scrutinize this with different kinds of skepticism. And so the cross-spectrum that you mentioned at the collaboration meeting here last year was with the Keck array data. And as the process evolved over the past 12 months, last fall particularly, we set for ourselves, because, as Clem says, the story that we're testing here with this data set seems so fantastical. We know it's good physics. But the extrapolation from the physics that we understand, combined with these models that have been built by theorists, to testable predictions that come from such an incredibly exotic regime at the beginning of our universe, we need a lot of convincing to believe that the signal was real. And the emotional process for us was helped by setting a series of concrete tests, milestones that the data needed to pass through the end of last year. And by last December, the data was passing each of those tests.
Frankly, if we didn't have this program of 3 very different experiments where we could cross-compare, I think we would still be scratching our heads.
Do we have any other online questions?
This question is from Miriam Kramer from space.com. Could someone please expand on why more evidence for inflation also hints at the idea of a multiverse? And then the question to Dr. Guth.
To me?
So that was to Dr. Guth?
Okay.
We'll get that microphone over there.
Okay. I'm sure Andre will want to weigh in on this also, so I'll give an answer and then I'll hand the microphone to Andre. But basically, the point is that inflation depends on essentially a kind of material that turns gravity on its head and causes it to be repulsive. We describe this material in terms of usually a scalar field. And in order for inflation to work, this metastable state of the scalar field in a peculiar position has to be stable enough to survive during the period of inflation itself. Which requires about 100 doubling times or so of the size of the universe. The process by which inflation ends is very similar to the way radioactive decay works. It's a probabilistic process. There's a half-life. And the point is that for inflation to work at all, the half-life of this metastable material has to be long compared to the doubling time of the exponential expansion itself. So in a nutshell, if you wait for a half-life of the decay of the material that's driving the exponential expansion, during that time, half of this peculiar material will have decayed, become normal material. But in the meantime, the volume of space would have increased by a much larger factor. So the total volume of the region that's inflating tends to just increase uniformly in time. And that's the simple picture, and one has to go to odd extremes, really, to avoid that picture.
And if I may add something, is that, well, just think about some unstable state. You are staying on the top of the hill, and then you can fall in this direction, or you can fall in another direction, and if you're drunk, eventually you must fall. So inflation is exponential instability of our space with respect to its expansion. So you have something growing exponentially. If you just let it go, if it does not go to the minimum, it will continue exponentially growing. So this is like one possibility of something going wrong, this instability, except for it's very, very right for us. So if, because it creates all our space, and now we know that if anything can go wrong, it will go wrong once, and the second time, and the third time, up to infinity, as long as it can go. At least we did have this experience back in Russia. So one way, and now this just brings us naturally to the idea of the universe when one part of it starts expanding and then it stops, so it becomes right. But there are some other parts where things go wrong and they continue expanding, and they produce some other parts where everything is normal, like around us. But the remaining continue go wrong, continue expanding, growing on. This process must go on forever. Thank you.
Thank you. We're running low on time, but we have one more question online.
This question is from Irene Klotz from Discovery News. What is the significance that the signal was twice what was predicted?
So
it was not operating the mean property.
Okay, yeah. So maybe we should clear up some confusion. I don't know that the signal that that's favored by our data, the amplitude of the B mode signal that we see, is twice what was predicted. The question probably refers to the fact that the interpretation of the existing data from the temperature of the CMB combined with the simplest model that we have of the early universe, I should say the standard model, lambda CDM, folding all that together implied a constraint on the expected level of the gravitational waves that was lower than the value that's favored by our data. But it's a very different kind of constraint. It's a very model-dependent kind of constraint in the sense that that's looking at statistical power on the largest scales in the temperature variations that we see in the microwave sky, and saying there seems to be too little of it already, not enough room in the power that we observe to add in an additional contribution that you would expect if there were gravitational waves. But it's a statistical argument, and it depends on model-dependent extrapolations down to those scales. So there could be many ways of resolving the differences apparent in that indirect constraint and the data that we're presenting today, which appears to directly show the signature of these gravitational waves at a certain amplitude.
There's also a considerable degree of uncertainty on the amplitude that we've measured, because we've only measured a small patch of sky. So we have very, very high sensitivity, but we only have a relatively small sample of sky. So there's, a value half as big as our most likely value is not that unlikely, right? So a value of 0 is extremely unlikely, but a value half as big as our maximum likelihood value is not that unlikely. So it may be that the tension is just a statistical fluke, and really it will just go away.
However, it is very interesting to follow it up. If we follow up and we tighten the error bar and it clusters around 0.3, then it makes it extremely interesting, because that tension will now be inconceivable, basically.
With that, I would like to conclude our news conference. I want to thank all of our presenters again, and thank all of you for joining us for this historic announcement. Have a good day.